afternoon, everybody. Again. It is a pleasure this afternoon to have our guest, Victor Debattista from the University of Central Lancashire.
I love the fact that you got my name correct, but not the name of the university. That's brilliant.
Lancashire.
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 Lancashire. Lancashire. Okay. It's not British, it's not anyway. So, a brief introduction to Victor. Victor got his PhD from Rutgers University in New Jersey in 1998. Then he moved back and forth. We mentioned it this morning from one side and the other of Europe and the United States. He got a couple of postdocs in Switzerland, Basel, and then Zurich. Then he was has been a Brooks Prize Fellow at the University of Washington. Afterwards, LCU Curie Fellow at the University of Central Lancashire.
Lancashire.
And then he became a professor at the same university, professor of astrophysics. And today, Victor is here. He will talk about hints of bar growth from bulges and density profiles. Thanks again, Victor, for accepting our invitation. And I have to give you 5 minutes.
Yes. Allora, grazie per l'invito. Grazie, professoressa o professore? Come si dice? Elisa. Grazie Elisa per questo invito. Professoressa. Ok, professoressa. Ma adesso in inglese, perché per me sarebbe molto difficile un'ora di seminario in italiano. So, yes, Victor Debattista, well pronounced. I'm going to be talking about these things called bars. These are features at the centers of galaxies. You remember from Hubble that when Hubble looked at galaxies, it classified them into the tuning fork, and there are 3 branches. There are the ellipticals. I have nothing to say about ellipticals. There are the spiral galaxies, and then there are these things down here, which are the bar galaxies. And I've spent a large fraction of my career working on these objects. These were the subject of my PhD, and I'm returning to some of the work I did for my PhD because it's becoming an interesting topic again. I will explain how. So when you see these things, you might think, okay, these are unusual objects. Why study them? There's a number of reasons to study them. First of all, it turns out that barred galaxies are the majority of galaxies, of bright galaxies. If we remember that elliptical galaxies are about 10–15% of all bright galaxies, the rest are disk galaxies. And of the disk galaxies, 3/4 of them have either a strong bar or a weak bar. And the majority of galaxies have bars in them of some sort. If we want to understand the Milky Way also has a bar. Our nearest big neighbor, Andromeda, also has a bar. So if we want to understand these objects, we have to understand bars. Bars, as I will tell you a little bit about, play an important role in the evolution of bulges. There was, for example, a very important review by Cormandy and Kennicott, sometime around 2000-something, 2005 maybe, where he talks about how most bulges that we see are in fact the effect of bars, not formed through the way we usually, things falling into the center. Bars play an important role in the evolution of disks. I won't tell you how today. I won't tell you why they matter for gas today also. But the important part is that bars also probe the dark matter halos of galaxies. We can't see dark matter directly, as you know. So it would be nice to find some way of probing dark matter halos. And then there's other reasons, but I'm not even getting into all the reasons why we want to study bars. But they are not unusual things. They are important to understand. So what is, a good picture of a bar? Here's an example. This is from the Hubble Heritage. NGC 1300. There is this very clear bar at the center. That is how Hubble Space Telescope sees it. Still sees it. And on the right is how the JWST sees it in the infrared. You see these dust lanes over there on the leading side of the bar are nicely resolved. in JWST's infrared cameras. And you will notice that there is not very much star formation going on there, but there's a little bit. There's a few star-forming knots over there. Probably what's happened there is that the star-forming knots formed over here, and they're still forming stars as they're falling inwards. Because what happens is the bar funnels gas to the center, to that ring over there that you see, and it's there that most of the star formation that is within the bar itself happens. So that's sort of a classic example of a barred galaxy to have in mind. This is our galaxy. This is the Milky Way. This is how, back in the days when I was still doing my PhD, the COBE satellites observed the Milky Way. So for the science, the main science that COBE was doing, it was studying cosmic microwave background. This was foreground, this was the noise. For us, that was really interesting because I wasn't working on the Milky Way at the time, I am now. When you look at that, you can immediately tell that there is a bar in the Milky Way. This had been stated many times before by the Vauquelin, Gerard de Vauquelin. Nobody believed him. He was arguing that there had to be a bar in the Milky Way because of the gas dynamics that he saw. Nobody believed him. They preferred to believe that there were big explosions at the center of the Milky Way. Then this came, and immediately became clear that there's a bar. Why? If I draw two lines over there, horizontal lines, you will notice that the left-hand side gets closer to those yellow lines than the right-hand side in the bulge. So what you're seeing there is just perspective. There's a bar, this side is closer to you, so this side is further away. It's a simple geometric argument that allows you to conclude the Milky Way, sorry, take that out. The Milky Way we live in has a bar. So we really need to understand. And the part that we're seeing over here is the bulge, the thick part of the bar, not the entire bar. The entire bar extends further out. Barred galaxies extend to redshift up to redshift 2. Over there, that's a barred galaxy. The fraction declines with redshift up to redshift 1, and then it stays flat. That is, as our current resolution allows us to conclude. It could well be that if we improve resolution, spatial resolution, because you can do this, from imaging, if we improve our spatial resolution, we might actually see a higher fraction of bars at our redshift. And here's an example of the joys of JWST instrumentation for people over here. This is just one galaxy over here. That's as it was seen by HST. It does not look like a barred galaxy over there. But then with JWST's fine imaging and views in the infrared, it becomes very clear that there's a bar in fact there. These sort of instruments, etc., that are happening over here, they have real important science consequences for this field too. So now the value I have here for one of the highest redshift is 2.3, but in fact I think we've gone beyond that at this point now too. So this is a movie. Let me show you how we think bars form first. This is the only movie that you're going to see. You're going to see the galaxy. This is the galaxy. This is a galaxy, as we would see it face on, and these are two edge-on views. You're going to see a bar forming there very quickly, and you will see this worked a few minutes ago. There we go. Let's move that out of the way. It starts out axisymmetric, and then there's an instability that develops, and that instability gives rise to this bar. It just formed very naturally in simulations. The other thing that you could occasionally look at is this. You will see a shape develop there. It loses symmetry about the midplane and then starts forming a shape like a peanut. That's something that in my group we study a lot. We've done a lot of work there. There you go. It's deviating ever so slightly from perfectly symmetrically, and it's starting to look a bit like a peanut shape. It's clearly thickened in the center, and that's being driven by the bar. There are two ways in which this happens, which I'll tell you about in a bit. In this case, you're definitely seeing a little bit of a bend, a small bend in the center. We refer to that bending as either a bending instability or a buckling instability. This is just terminology we use. You can just think of it as a bending. You can see how asymmetric it is at the moment. It goes through periods where it's asymmetric with respect to the midplane, and then you get this thick bit in the center, but it's only in the inner half or so of the bar itself that you get the structure. So the bar will extend further.
So is it what quantity? The density?
This is the density we're seeing here. We're projection of the density.
But of gas?
Of stars. This is just stars. This is purely stars. This is a simulation with no gas.
Okay.
So when we introduce gas in simulations like this, the evolution changes, but we have problems with properly following everything that bars do. For one thing, if you look at cosmological simulations, for instance, you don't form them. And we still don't understand why that is. I'm not going to talk about that today, but that is still an open problem.
Because I remember when I was a PhD student, say in Pisa, Scuola Normale Superiore, and I was following a course in this, the ring theory, that explained the spiral arcs, not necessarily the bar, as a compression, as a wave that travel. And where the shock forms, the gas is compressed, and there you form stars.
That's right.
So we see the spiral arm as the side where more stars, especially the brightest star, the more are concentrated. But this is also true for.
This is not true for bars. In spirals, that's a wave that propagates and eventually dissipates. These things don't dissipate in the same sort of way. These trap stars, so the stars are living within the bar and moving up and down along the bar. That's not what spirals do. Spirals, it's a wave, and they slow down in the wave, but then they continue on their way. That's the difference between bars and spirals. We don't want to see that again. Now, you saw when I showed you that movie that the bar is rotating. We can measure how fast the bar is rotating. The way you do that is, if you have your galaxy, in the old days, you would take slits parallel to the major axis. For each of those slits, you measure the average position. You measure the average velocity. You plot those two against each other. And what comes out is a straight line. And the slope of that straight line is proportional to omega p. Omega p is the pattern speed. It's the angular frequency of the bar, how fast it's rotating. Okay, so we can measure that. And this has been done. Let me define for you what a fast bar versus a slow bar is. When do we talk about a bar being fast or slow? So first of all, imagine yourself, we had the bar that was rotating. Let's put ourselves in a reference frame which is rotating with the bar. So the bar is now at rest with respect to us. As you know, when you're in a frame like that, physics 101 or whatever the equivalent is in Italy, you have a centrifugal force, and then you have the gravitational force. Where those two balance out, you have what's known as a co-rotational resonance. So stars at that radius or at that location are not circulating around the bar in the reference frame of the bar. They just stay in one location only. They don't go all the way around the bar. Okay? That is what's known as co-rotation. Another way of looking at that is if we have the rotation curve of the galaxy, each of these lines correspond to a bar of different patterns, different angular frequencies. Why? Think of the bar like a solid object. If it's rotating like this, the speed at which it's rotating at each location is just solid body rotation. B is equal to omega r, right? So if I draw a line with slope omega, or omega p as I've written it, that is a line that corresponds to a bar rotating at the angular speed omega p. Okay? And so then this is the co-rotation resonance, where this line intersects the rotation. Stars at this location do not go all the way around the bar. They would, if this is the bar and I put myself in the frame of the bar, they would do something like this. They're not doing this. Okay? They stop doing that at the co-rotation resonance. They do this like this. Okay? So, whether a bar is fast or slow is a comparison between the size of the bar, this vertical line, which is labeled AB, the semi-major axis of the bar, and the co-rotation resonance. And there are three regimes in which we can think of. One is when the co-rotation resonance is within the bar itself. And that, from orbit theory, is forbidden. And the reason for that is because if you're in this regime, the orbits, instead of being aligned like this, are aligned like this. And you cannot build something aligned like this with orbits aligned. I'm not going to explain the details of that. It's reasonably complicated. But this region is basically all forbidden. The bar cannot have a co-rotation resonance inside it. This is the way to think about it. Then there is the bar which ends just inside the co-rotation resonance, or very far inside the co-rotation resonance. Okay? Those that end very close to the co-rotation resonance, they're almost as large as they can be, and we refer to them as fast. Those that end well inside that point are what we call slow bars, because they can be much larger, basically, is one way to think about it. Or because the pattern speed to the angular frequency can be much larger. Okay? Just, it doesn't matter the details of exactly what the limits are. There's some limit that we can define. Now I told you before, we can measure this. One of the first things I did as a postdoc, on my first postdoc, was actually build a collaboration that measured these pattern speeds for a lot of galaxies. It was Alfonso Guerri, myself, and Enrico Maria Corsini, and part of us, we called ourselves the Ave Maria collaboration from our first mission. This is the size of the bar. This is the co-rotation radius. This is the 1-to-1 line. This is 1.4. This is sort of the regime of fast bars. This is the regime of slow bars. And you notice within these error bars, these are not error bars in the sort of 1 sigma sense. These are error bars in the size, for instance. That's the full uncertainty on the size of the bar. Okay, this is how we plot it. They're consistent with fast. They sometimes reach into the forbidden region, which gives you a sense of some of the systematic effects we're not really fully accounted for. But it's remarkable how close they lie to this region. Observation, this plane has now been populated by many more galaxies, and predominantly, to a large extent, bars are fast. Okay, fine, whatever. Why is that interesting? It's interesting because what my PhD was about was using bars to probe how much dark matter there is. Imagine yourself, you put yourself on a bar stool, one of those that rotate, okay? And you start spinning yourself. If you do that in air, you'll spin till you're dizzy, right? If you do that in water, you slow down very quickly. Why? Because there's friction. You're losing angular momentum to the water. The bars, stellar bars, are the same. There is something they're immersed in. They're immersed in dark matter. So they lose angular momentum to the dark matter. And the more dark matter you put there, the faster they lose that angular momentum. Okay? So if you parameterize in some way the stellar contribution to the rotation curve, you have on this side, the dark matter dominates. On that side, the stars dominate. And you ask what happens to these bars after some time. When the dark matter dominates, you end up in this regime with very slow bars, in the regime where we don't observe the galaxies. That would correspond to being out here. Whereas when there's very little dark matter and you're dominated by the stars out to sort of, let's say, the solar radius, you end up fast, consistent with observation. What the dark matter does is it slows down bars, so we are actually able to determine how much dark matter is. Because I remind you that when we look at real galaxies, we measure one function we measure one quantity as a function of radius. We measure the rotation velocity. But we don't know whether the amount of dark matter that satisfies that is given by this line or by this line. Here, the dark matter dominates the rotation curve everywhere. Here, it's as low as it can be, what we call the maximum disk. Okay, so there's a huge range of mass to light ratios. This is a mass to light ratio of 0, the mass to light ratio of 2.3. And they're equally consistent with what we observed. And that's because we're trying to fit one function, one one-dimensional function, with two one-dimensional functions. And that's a degenerate problem. So we can't tell how much dark matter is. But this gives us a way of telling that. Is there too much? Is there not too much? Is there a lot of dark matter, or is there little dark matter? And so this is why this was an interesting thing to do. And so the prediction was from this sort of work, from this observations and then the simulations, that the bar will form in this regime. But if there's a lot of dark matter, the bar grows, but it also gets slow. And you end up in this regime of slow bars. And that's not what's observed. And this has been true now for decades. My PhD was 98. It's been true for decades. We haven't fully understood completely why so many bars are consistently fast. I know of one very clear case of a slow bar. And, that looks like a small number over there, but now we have of order of 100. So why is that happening? The other thing that I said, of course, over here is that the bar slows down, but it also grows. And when you do these simulations, sometimes these bars get really big. You will end up with bars with a radius of 10 kiloparsecs. That's huge. This is some work that Peter Irwin did. I'll talk about that in a bit, about the time in a bit. This is as a function of mass, how big are bars in a statistically significant sample, in the sense of it's a complete sample within some distance. And you see that bars don't get to be very, very, very large. Even in the mass range of the Milky Way, for instance, the bars are a few kiloparsecs across. They rarely get to be 10 kiloparsecs across. In the Milky Way, the bar is about 5 kiloparsecs in radius. Not huge. This is Peter Irwin over there. You might recognize me. This is a conference I organized a few years ago when I first moved to the university. I'm showing him here. I've done a lot of work with Peter. Peter, unfortunately, recently passed away. So we are, if any of you are interested at all in bars, we are organizing a workshop in his honor next year in the Aeolian Islands. I don't need to explain where that is to this audience. I'll be talking about work that together the two of us have done. In part is driving. Right. So how do we solve this? Well, one possible solution that's been suggested is that maybe the barred galaxies preferentially live in dark matter halos that are less dense than the average. So these are the dark matter halos in which, in the Auriga simulation, the bars are forming. They prefer lower density halos. You see, this is what the observations are saying. This is what the Auriga simulation finds. It finds fast bars, whereas other cosmological simulations, Eagle and Illustris of those, I think, are finding slow bars. So, in other words, the claim here is that barred galaxies live in different environments from unbarred galaxies. One of the problems with that, or the problem with that, it needs to be reconciled with the fact that the Tully-Fisher relation of barred galaxies is the same as that of maybe true, but this needs to be, still needs to be reconciled. It's not been demonstrated. Okay, so it looks like bars are fast. Does that mean that bars never slow down? Because if that's what it meant, that would be strange. Because there is dark matter, right? We cannot find in the universe evidence of bars slowing down. Well, that has changed quite recently from the work of Rimpley Chiba in the Milky Way. Because we have Gaia, we can study the kinematics of stars in the solar neighborhood very well. And you see, rather than just being a Gaussian, a two-dimensional Gaussian, this is radial velocities along this axis, tangential velocities on that axis, rather than the distribution being just like Gaussian, there's lots of features in there. And those features are formed by stars being trapped by the bar. And the stars aren't just trapped by the bar. If you have a model of these are solar neighborhood stars. Of solar neighborhood stars trapped by the bar, if the bar is not evolving, there aren't very many features in the distribution. It's essentially a two-dimensional Gaussian. But if the bar is also slowing down, what the bar then does is it captures stars, it pushes the stars out. And then you start being able to form those sorts of features. But this is the first evidence of a bar slowing down anywhere. It's in the Milky Way, and we can only do this kind of work in the Milky Way. Okay? What about other galaxies? Okay, that was my introduction. I hope I've given you a nice introduction to the subject. Now I'm going to tell you a little bit about the work we've done. So to do that, I'm going to step back a little bit and return to the subject of these boxy peanut bulges. This is an example of one such bulge. We now know with high certainty that when we find one of those bulges, if we do an unsharp mask, for example, there is a clear X shape, including in the Milky Way. That means that in the center of this galaxy, there is a bar. This connection has now been made very strongly. And we know of two ways to do this. This is the one I showed you before, where the galaxy, the bar is bending vertically. Okay? The other way is that the bar slowly evolves, it traps stars at resonances, at vertical resonances, and those stars then levitate to large heights. So the disk starts out, uniformly thick as a function of radius, but then as time passes, you form this progressively, the different lines here are different time, you form progressively thicker bits near the center of the bar. There are two mechanisms that have been explored, and they're well understood. Now, I said before that, the early studies of these box peanut bulges are edge-on. The problem with edge-on galaxies is we can't study the bar, and we can't study the galaxy very well because we're seeing a galaxy edge. And that's an awful way to study galaxies. So one of the things I did with Peter was we developed a way of identifying box peanut bulges, not edge-on, but in inclined galaxies. And the way that works is if you have a galaxy and it has a bar, if you zoom into it, this is not particularly high resolution necessarily, there's a region that is boxy at the center, and then you see these spurs, these fingers, and if you draw the major axis of the box, this is the major axis of the box, this spur is offset upwards relative to it. This is what in elliptical galaxies we would call isophotal twist. The isophotes aren't all aligned, the isophotes twist. And the reason why there's an isophotal twist is because you have a shape, you have a common axis, but the shape it's triaxial, but the shape is not the same at all right there. The shape changes. So it's thick over here, and it's thin in this part. And it's about the right size, given the simulation. This is the box peanut bulge bit. This is the rest of the bar. So this means that we can, from a local sample, study how often these box peanut bulges happen, because we can observe these easily. And this has been done. We've done this with data from the Spitzer satellite, and what we get is the result on the right-hand side over there. We find that the probability of any barred galaxy having one of these box peanut bulges is 0 for low mass galaxies. This is 10 to the 9, 10 to the 10, 10 to the 11, 0 at the low mass end, and 1 at the high mass. It's a step function, which really puzzled us for a very long time. Why does this happen? The Milky Way, in case you're not familiar, is the shaded yellow region. The Milky Way has a very high probability. It has a bar, so it's got a very high probability of having a box peanut bulge. And that's actually what I was showing you before. The thing that I called the bar before is, in fact, the box peanut bulge of the Milky Way. and that means there's a thinner bit that is extending further. We can also identify galaxies that are going through this bending phase. Let me not waste time on that at this point. Let's first try to understand what is happening, why this is happening. Why is there this mass dependence? And the way you can do that, I mean, my initial thoughts were completely wrong. My initial thoughts was gas. It had to be gas. And what Peter did was he persuaded me by looking carefully at the observations that no, it could not be gas. So what we then eventually decided to do is there are big cosmological simulations available. Illustris TNG is one example. We took Illustris TNG and went looking for these box peanut bulges in there and asked, when we find those, don't worry about the details of how we find them, what do we find? We're able to find them quite commonly. If we plot observations, those are the open circles and the box peanut bulges in our simulations. Those are the squares, the green squares and the red triangles. The distribution matches. We have to make a cut on bars smaller than 2.6 kiloparsecs. This regime is not very well resolved in TNG50, so we can't probe this regime. But when we do that, our distributions look very similar in terms of bar size versus mass. And then when we ask the question, how does the box peanut bulge fraction depend on the mass of the galaxy, we get a very similar function. It rises rapidly. We can't go to very low masses, so we can't see the zero bit. But in the region where it should be rising, we get a rise at about the same place as we were in the real universe. We don't get a fraction as high as in the universe. This is the universe, 100% over there. This is the simulation, that's 60%. We don't get as high as observed, but the behavior is similar. So that allows us to now ask the question, why this mass dependence? Why does it rise from essentially zero here to some large fraction? And to answer that, we looked at the time at which bars form, and this was the one thing I hadn't thought of before. When did the bar form in the evolution? The low mass galaxies are forming their bars relatively late. The high mass galaxies form their bars very early. You know, this is after 4 gigayears of cosmic evolution, essentially. So these bars, these massive galaxies, form their bars early enough for the box peanut bulge to form, whereas these ones are forming their bars so late they don't have time to form a box peanut bulge. This is, in other contexts, what people would refer to as downsizing. Contrary to what we would expect, although the universe we live in is hierarchical, so we expect the small things to form first, and then bigger and bigger and bigger things to form later. Star formation within galaxies works the opposite way around, and that's because of feedback. Feedback slows down the formation of galaxies, so the low mass galaxies are still forming stars now. They're still not at their final mass that we would expect. They still have a high gas fraction, whereas the high mass galaxies form their mass very fast. And the star formation in the Milky Way now, for example, is starting to wind down. There's also a relatively low amount of merging that happens. This is true in TNG50, but it's also true in other simulations. This is the Auriga simulation that I was showing you before. Those galaxies that are going to go on to form a box peanut bulge, predominantly it created only a very low mass of stars from external galaxies. Whereas galaxies that never formed the bar, up to 1/4 of their mass, came from external galaxies. This is the difference. These are more quiet galaxies that form their mass early. And we can sort of our understanding of these box peanut bulges is now at the level where we can make predictions. We can make detailed predictions. This is some detailed predictions I made back in 2017 about what the age distribution, if we were to look at the Milky Way bar, would look like. We're looking at it from the side, right? Because we're within the disk. So this blue stuff, those are young stars. That's the disk. That's not the interesting bit. The interesting bit is what happens away from the plane. And what we predicted was that the oldest stars are on the strip. And then there are two brackets, one there, that are slightly younger ages. That's purely simulations. Gaia can track stars known as Miras. Miras have a relation between the period of the Mira, they're variable stars, and the period of the variable of the Mira anti-correlates with the age. And so you can recover an age, in other words, or even if you don't recover the age, you can recover an ordering of the period. And when you do that in the Milky Way, you find the oldest stuff is in the center. There's a bracket here and the bracket on the opposite side, exactly. That's predicted by the model 3 years before. Okay? But with completely different groups, this is not the same. We can also predict the metallicities. This is, again, simulations. We predict that the metallicity, if you look at one of these box peanut bulges, the red contours here, which I hope you can see, they look boxy, okay? But if you look at the contours of the contours of the metallicity are more pinched. They're more peanut shaped. Okay, this is this galaxy. We took a map of its metallicity with Muse. The density contours are the dashed ones, and then the metallicity contours are shown by the solid lines and by the colors. The metallicity distribution of this galaxy is more pinched than the density. And this is sort of telling us that the prediction that we have here is borne out in the observation of this galaxy. So we were able to understand them to quite high detail. Right, so that is one bit. Let me show you another bit of evidence, the density profiles. If we have a bar and we look at the density profile along the major axis of the bar, and I'm going to go a little bit faster because I've been going a bit slow. If we plot the profile, we'll see something decreasing, and then there's a bump over here. And we started calling that a shoulder profile. So we studied this in simulations. With Peter, we classified a sample of order 181 galaxies, and we classified them into those that have shoulders and those that don't, okay? The rest of them are basically all purely exponential, except at the very center. And we then look again at the mass distribution of this feature, whether you have a shoulder or not, okay? And that's shown by this open histogram. The number of galaxies that have bars, these all have to have bars, and have a shoulder is shown by the solid line there, the solid black line. And what you'll notice is that most of them prefer the high mass galaxies. Most of them prefer the high mass galaxies. This is Peter's classifications. This is done by eye, so we decided to do 2 of us so that we can have some statistics, as it were, or some sense of errors, not statistics. And if we plot the distribution of these shoulders as a function of mass, we have a function like before. 0 at low mass, 100% at high mass. What's also very interesting was that what this dashed black line is, that's the function, this probability, for the bars to have box peanut bulges. Not to have shoulders, but to have box peanut bulges. So if you think of galaxies, most of the time when they're forming, their mass is increasing. So a barred galaxy will first form a shoulder, and then it will form a box peanut bulge. So you think of it as evolving this way, right? You have a higher probability of forming your shoulder profile before you form the box. So why is that? Again, it's something begging to be understood. So again, we went looking in simulations. We developed an algorithm for finding these shoulder profiles. We find lots of them. This red stuff is where the shoulders are. Not going to go into the details of all that, but we're able to measure shoulders, and we quantify the strength of the shoulder by the excess mass in this region. Okay, this is the profile on just one side of the galaxy. What is the excess mass above a pure exponential? Okay. And when we plot that, when we plot the evolution of that shoulder, the time evolution of that shoulder, it correlates with the growth rate of the bar, the size of the bar. It's got scatter, it's got lots of scatter in it. There's still things to be understood there, but there's a fairly strong correlation. And we think we are now able to understand what causes these shoulders. If we go in the region in the simulations where we have the shoulder and we isolate the stars over there, and we ask where are those stars a little time later, they form these very characteristic orbits, which are known as what's known as the X1 orbit, the looped X1 orbits. It doesn't matter the details. They form this kind of structure. Okay? And that's what supports the shoulder. Now, let me introduce one last thing, and then with this, I'll be able to finish off my talk, basically. We are going to now look at stars in these simulations to understand how they evolve. And what we do is, for each star in the simulation, we compute an orbit. And once we compute the orbit, we can measure the and we're going to do this in the rotation frame of the bar, in the rest frame of the bar. Okay? We will have three frequencies. We will have a frequency at which it oscillates radially, the frequency at which it oscillates vertically, and the frequency at which it goes around the bar. So this is the frequency at which it rotates around the bar, divided by the frequency at which it oscillates radially. And this is the frequency at which it oscillates vertically, divided by the radial frequency, the frequency of radial oscillations. Okay? And you will see that these colors here represent different stars in the simulation. Never mind the colors. What you want to notice is that there's a whole bunch of lines in there. And those aren't lines that we've drawn in. There's some lines that we've drawn in. But there's also a whole bunch of lines without us drawing anything. What those represent are what we call resonances. Working on planetary physics, we'll know that these things happen a lot. It's possibly why Saturn has so many moons. And the barred galaxies force exactly the same sort of thing. I want to focus on two resonances in particular. This horizontal one here at the top, that's what's known as the inner limblad resonance. Stars at inner limblad resonance oscillate radially twice for every time they go once around the bar. Okay? And then there's this resonance, the vertical inner limblad resonance. And there, stars oscillate vertically twice for every time they go once around. And these two resonances will turn out to be very important for the story that I want to tell you. So we start off by taking one of our simulations that has these shoulders. That's what this red stuff is. And we compare it with one that doesn't form shoulders. And we ask what is going on in there. And we can take the inner limblad resonance, this horizontal line at the top, and we break it up into three chunks, this, and this, and we label them cool, warm, hot, for reasons you'll see shortly. And we ask, what do the orbits look like there? So for orbits like number 3 in the cool region, that's what they look like when we see them from above. In the warm region, they look like this. Do you remember that? Exactly the same shape. These stars, these orbits are what is producing the shoulder region. And then the hot ILR orbits look like this when seen from above. And those are more chaotic. They don't very strongly support the shoulder region. This is this is just one orbit up there. This is if we take all, if we take all the orbits there, and you see that these warm ILR strongly support the shoulder. That's when we see it from above. When we see it from the side, from this direction, with the bar side on like that, these are very thin. The cool ILR is very thin. That's why we call them the cool ILR. This is slightly thicker, but then these guys, the hot ILR, gets very thick. And in particular, you will notice immediately a peanut shape. What seems to be happening is that as the galaxy evolves, what will happen is that the bar slows down and it also gets larger. So that gets larger, pushes stars this way, and slows down means omega p decreases, so that increases. So you're pushing stars in that direction relative to the resonances. And that will deposit some stars on this inner limb-like resonance, and then some of those stars will cross the vertical inner limb-like resonance. And so what ends up happening is, that's what's coming here. I'll remind you here again, this is the effect of the bar getting longer. This is the effect of the bar slowing down. Okay? And so let's just go to this one. We pick a bunch of stars that at 7 gigayears are part of the shoulder. And we ask, where were they at 5 gigayears? At 5 gigayears, they're nowhere near this resonant line yet, or past this resonant line. As the bar slows down, they're pushed this way. At 7 gigayears by construction, they're on that resonance line. At 8 gigayears, they've now crossed this resonance too. Some of them anyway, not all of them. And the same at 9 gigayears. So they've also thickened vertically. So what does that mean? You get here first, you get to this resonance first, the inner limb-like resonance, which gives you the shoulder. And then you the bar slows down further, and you start forming the box peanut bulge after. And that is what gives you this seeming timing of forming the shoulders first, and then the box peanut bulge. And that's the story, basically, that I want to tell you. What's left is just the future. We're eagerly anticipating DR4, so we can do this more in detail in the Milky Way. Also, more in detail in the Milky Way. We are part of the Moon's collaboration. Thank you for developing infrared imaging technologies and spectroscopy technologies. This will give us a huge amount of data, 500,000 stars in the inner Milky Way, which is really useful for this sort of stuff. And then to go out to the rest of the universe, we are part of Euclid, and we will be looking for these kinds of signatures in real galaxies. And this is Euclid, we can find bars at high redshift, that's very recent. And that's my conclusion, so I'll stop there. Thank you.
I'll stop the recording as promised.